Alas, I return, this time with more knowledge. So previously, we had looked at flight path angle. Now, I want to talk to you a little bit about specific orbital energy, which, if you remember from the specific angular momentum video, should be the lowercase letter of the energy. However, lowercase e is reserved for something else, so we will not be using it. You'll be seeing that one a little bit later on. Instead, we're going to use epsilon. Now, let's take a minute to talk about the different types of energy, because they all technically interact with one another. So you have your kinetic energy. This is the energy of a body moving along a path. You have your gravitational potential energy, which is just the higher something is, the more energy it has, the more potential it has to hit the ground harder. You have elastic potential energy. This would be energy stored in a spring or spring-like substance. You have rotational energy, which I am putting distinctly different from kinetic energy. And I'll tell you a little bit about why. It is because whereas kinetic energy is the energy of something moving along a path, the rotational energy is referring to the amount of energy stored in all the bits, bobs, and particles that are orbiting, I shouldn't use the word orbiting, that are rotating around the center of mass of the body. Now, kinetic energy and rotational energy are largely coupled together. See also why the moon is moving away from the Earth. But we're not going to be talking about that today. In fact, there are a whole host of other energy sources like thermal and chemical and a couple of others that immediately spring to mind, and probably more besides. But we're not going to be talking about any of them because we're going to make some assumptions, namely that the satellite is a point mass. It has nothing rotating around the center of mass of the body because it is the center of mass of the body. And so that's why the rotational energy specifically, even though that is technically a form of kinetic energy, we're not going to consider it. These other two, kinetic and gravitational potential, are linked together. Whoops. Sorry about that. They are linked together. So we will take the time to look at them individually. We're going to start with our kinetic energy term. If you remember from your Physics 1 days, that is going to be mass times velocity squared by 2. Simple enough. And then if we look at our potential energy, that should be mass times gravity times height. Make that look more like an H, times height. And that would be accurate. That would be true, were we not dealing with truly astronomically large distances. Because not only does the height change, but so too does gravity with that height. So let's rewind a bit. I'm going to look at the definition of energy, which is going to be the force dotted with the distance of the force. So the amount of oomph given to a thing and the distance in that direction that it travels. And that is going to be your energy term. So we break that down. We know what our force is because we derived it in the first episode as G mass of the Earth, mass of the satellite, in the direction from the center of gravity of the, in this case, Earth and satellite system, the center of gravity of that system, divided by the magnitude of that distance cubed. And it's dotted with the distance. And the distance, in this case, is going to be the radius from the center of the system to the satellite, which happens to be our R vector. And so carrying that onward, just as before in the specific angular momentum episode, when you see a value crossed with itself, it becomes 0. Here, when you see a value dotted with itself, not only does it become a scalar, but it is squared. It is the square of that magnitude. And since I wrote the distance as a scalar up there, I'm going to write it as a scalar down here. We can see that we have terms canceling. So there you have it. Minus g times the mass of the host body times the mass of the satellite divided by the distance between them. Effectively, the distance between them. So we combine it all together. Mass of the satellite, speed squared by 2, minus g, mass of the Earth, mass of the satellite, by the distance. And if you further remember from the specific angular momentum episode, this is mass specific. This is per mass, per unit mass of our satellite. So let's get rid of the satellite mass terms. Squared by 2 minus g mass of the Earth by r. And this is, once again, not quite the whole story. Give myself a little bit more room here. This is not quite the whole story because, if you remember from the first episode, not only is the satellite falling towards the Earth, but the Earth is falling towards the satellite. They are falling towards their center of gravity. So again, really what that looks like, it's going to be like this. We need to take into account that both bodies are falling towards their center of mass. We have already assigned a character to that, mu. So to wrap it up, make sure that looks more like a v squared by 2 minus mu by r. And there you have it. Our specific orbital energy, which happens to be one of those constants of motion that I had mentioned earlier. So let's make sure that it is. We're going to take the time derivative of both sides. Yep. Time derivative. And I'm going to write my v in dot notation. So r dot squared by 2 minus mu by r. Very nice. Left side, easy enough. E dot. Right side. So let's take the 1/2 out because that's a constant. And then r dot squared. R dot times R dot. And when we take the derivative of it, we know that it is going to be the derivative of the first times the second plus the first times the derivative of the second. Then for the second term, we can take out the minus mu because that's constant. And I'm going to treat my r as r to the minus 1, taking the derivative of that. It's going to be that minus 1, that exponent, the derivative of the variable over the variable, and then reduce the exponent by 1, so 2. Continuing on, we have 1/2. And then these two are the same. So we can say that it is 2 times r double dot times r dot minus mu. Let's make that look a little neater, shall we? Mu is r dot over r squared. Well, this cancels with this, and this cancels with this. All right. So we remember what our acceleration is from the first episode, the introduction to the two-body problem. And that is going to be minus mu r over r cubed. And I'm writing it in vector notation here. Not vector notation, in scalar form here. Hey, how's it going? You enjoying the video so far? Great. I want to take a moment to explain why I am using scalars over here instead of our vectors that we had been using before, because I didn't quite like the way that I worded it in the original pass of the video. So the reason why the short version is that I only care about the magnitudes. And as such, I'm only going to use the magnitudes, which is why nothing here has the little arrow over top of it. The slightly longer version is that I am using the dot product between the multiplication of the acceleration vector and the velocity vector, rather. And that is basically a longer way of saying the same thing. I only care about the magnitudes of it. R dot plus mu r dot by r squared. Well, we have an extra r up here that can cancel with an r downstairs. Minus mu r squared plus mu r squared r dot. And here's an r dot over here. It turns out that cancels off. Therefore, it's 0. We have no change in energy with time. It is, in fact, a constant of motion. All right. So now that we've proven that it is a constant of motion, let's go ahead and do an example. Let's do an example. And I'm going to say, let's do the exact same example as we've been doing before. Our same given conditions. It's going to be 16,065.4 kilometers, and our r dot Hello, pen. Would you like to work today? Thank you. 5.345550 kilometers per second. All right. So we have these things. We have our distance and we have our velocity. So if we rewrite our our equation, because we want to know what all we need for it. C squared by 2 mu over r. We know what our distance r is. Let's make that look neater. Much better. And we know what our velocity is. That is 5.5 kilometers per second. All right. But what's mu exactly? And I don't think I've actually given you a formal number to work with. So let's go ahead and do that now. We know that, give myself a little bit more space. Mu is equal to G mass of the Earth plus mass of the satellite. And 2 of these 3 values we can look up. In fact, I will do that now. G is 6.673 times 10 to the minus 11th meters cubed per kilogram second squared. Before I give anything else about it, I just want to point out that, yeah, that seems like a bit of a weird unit to have there, right? You have kilograms in the denominator along with seconds squared. It's kind of weird when you think about it. Well, that is one of those fancy schmancy constants of the universe that's, yeah, it's got a bit of a weird unit set here, but it does that so that you can put in reasonable units in reasonable spots and you can get a reasonable thing out. So you put mass in, you put distance in, you can get force out if you use this. Long story short, don't worry about it too much. That kilogram is going to go away. Times 10 to the 24th kilograms. All right. So we know what 2 of these 3 things are, right? We know gravity, you know what gravity is, we know what the mass of the Earth is, but we don't know the mass of our satellite. I am going to make the argument that it doesn't matter. So let's pick a number. Let's pick a number for a reasonably sized satellite, or even an unreasonably sized satellite. Let's say 3,000 kilograms. I'll use the same notation. 3,000, 3 times 10 to the 3rd. All right, well, this number up here has 21 more digits before the decimal, before the mass of our satellite. Our satellite's mass, even though we picked a number that is thousands of kilograms, it is huge. It is non-existent to the Earth, effectively. It is not even a percent of a percent of a percent. And that means that we can ignore the mass of our satellite for this. So U equals, I'll tell you what, We already know that G goes into it, and mass of the Earth is going to go into it. So I'm not going to write them out. 3.986 times 10 to the 14th meters cubed per second squared. And if you aren't already writing out your units, this is why. This is why you should. I don't like two things about this. First, I don't like that that number is so big. It is still billions and billions of meters cubed per second squared, but that's the other thing. I don't like having meters in an equation where I have kilometers. So let's neaten that up. Let's neaten that up some. 986, that's not going to change. 10 to the, and so a meter is 1,000, or a kilometer, if I can speak, a kilometer is 1,000 meters. Do that 3 times. 3.986 times 10 to the 5th kilometers cubed per second squared. So underlining that. All right. So now we have all of our components here. We have radius, we have our velocity, and we have a gravitational parameter. Let's plug it in. Already, let's get it wrong. 5. Let's also do this, because I just made a big deal about including your units. All right, so we have some upkeep to do. We have a kilometers in the denominator over here, and we have a kilometers cubed in the numerator up here. Just gonna do kilometers squared per second squared. That's gonna be kilometers squared per second squared, which means that our orbital energy is gonna end up being kilometers squared per second squared. And I'll write that down here in a second. Kilometers squared per second squared. Very nice, right? We have an answer. But wait, I hear you cry. Why is our energy negative? Why do we have a negative energy? What does that even mean to have a negative energy? I'm glad you asked. That is because, and I'm going to explain it in 2 different ways. That is because, in part, our equation consists of a kinetic term and a potential term. And the potential term, if you'll note, is negative. That means that in our system, we have something that is, I'll save that particular description for just a second. That means that in our system, our gravity term is dominating the kinetic term. And what does that mean? Oh, here's the second way of explaining it. That means that if we have our satellite orbiting our planet here, gravity is keeping it in towards the planet at all times. It does not have enough kinetic energy to get out and away from the planet and fly amongst the stars. So, when our specific orbital energy is less than 0, we have an elliptical orbit. And if we have a specific orbital energy that is greater than or equal to 0, we don't have that. We have, instead, the satellite that goes flying out away from the Earth, past the moon, past the sun, it just goes flying. It just goes. And that's something that we're going to take a look at later. But for right now, we are going to focus primarily on elliptical orbits. And I think that's a pretty good spot to stop it at. Thanks for stopping by.